Okay, so today I'm going to talk to you guys about why thermal simulation is a must for electronics design. And to answer that question, we first must begin with modern electronics. Modern electronics are ever increasing in complexity. It's not uncommon to have 12-layer boards, if not more, each of which can have hundreds of components, thousands of nets. Power densities forever increasing, and we're processing higher frequency signals. When designing a PCB, different people will consider different things. So you'll have your electronics engineers concerned about signal integrity, electromagnetic compatibility, do things need electromagnetic shielding, things like that. And then you'll have your mechanical guys who are interested in things like weight, size, cost, is it possible to manufacture a certain shape, and things like that. And what people don't often consider is that each of these different design considerations is intrinsically linked to thermal. So if you don't consider thermal from the start, and you make decisions relating to one of these areas, then later on in the design process realize that thermal is an issue, it can be difficult to go back and reverse one of these design decisions that has already been made. Why is thermal design critical? Well, there are three main reasons: performance, reliability, and safety. In terms of performance, as you all know, devices often have to employ throttling to manage component temperatures. So if you consider a mobile phone, for example, it's pointless having a powerful device that can only run at maximum performance for a couple of seconds before the chip has to be throttled. Users would notice this negative impacts on performance, and this could have an impact on your brand reputation. Same with reliability. Will the products fail prematurely? If you were to buy a mobile phone, you'd be disappointed if it failed in 6 months. And as we all know, thermal issues are one of the major causes of reliability problems. And finally, there's safety. If you have something that's handheld or designed to be touched, touch temperature needs to be safe for a user, and there's sort of various international regulations that you need to meet depending on the material, and also to a lesser extent there's risk of fire. Your brand would definitely take a big hit if you released a product to market and it caught fire. A few years ago, as a company, we surveyed over 300 engineers across the industry in a report we released called The Heat Is On, and we found that 45% of an engineer's top priorities is reliability. I'm not sure what the remaining engineers were concerned about, but these 45 wanted the products to be as reliable as possible. However, 33% of engineers say they need to spend more time on thermal management, and 27% of people wait until after a design has been completed before they consider testing for thermal issues. Now, that's a pretty crazy statistic if you think about it. 45% of people want reliability, but 27% of people are ignoring thermal until after the design has been completed. So, as you all know, overheating electronics are a major cause of reliability issues. 99% of the engineers we surveyed had had a project delayed by late stage complications, and 20% of people identified thermal as the cause of these issues. And the average cost people put on a late stage design failure was around £20,000. So, when do engineers test the thermal management of their designs? 23% of people say they're doing this early in the design process. They're considering thermal right from the outset, even before they've built a prototype. 50% of people say they consider this after the first prototype. So at this stage, they might not have paid for things like tooling. They could just be using a test PCB placed in a large box, for example. And 27% of people say they're doing it after design is complete. So by this point, they could have paid for tooling, manufactured custom enclosures, and at this stage, things can start to get really expensive. So how much is the cost of redesign? Well, to put some figures on it, a small run of test PCBs could be in the order of £2,000 to £3,000. A similar figure could be put on custom enclosures, and if you don't have your own facilities to do laboratory testing, for example, you're looking at £1,000 per day for testing. Plus, on top of that, you've got all the money you've paid your staff or any outside consultants to reach this point in the design process. And here's just a nice quote from the CEO of Lascar Electronics, who says that tools that enable design checking should be deployed at the earliest stage. So, as engineers, how do we go about avoiding the cost of redesign? Well, the key to this is to incorporate thermal simulation into the design process as early as possible. We'll talk a bit more later about simulation-driven design, but here's a nice quote from Dr. Sackett at Facebook. He says that given how the electronics industry is changing, we now have to start modeling simulations at least 3 to 4 years in advance. And here is just one final thought. What is it that consumers expect from products? Well, typically that is lower cost and high reliability. As Dr. Sackett goes on to say, everybody wants things at a lower cost and with high reliability. This puts more burden upon design engineers to find good solutions. And yeah, that is where simulation tools are going to come in. So let's move on to talking about thermal simulation. So what is thermal simulation? Thermal simulation allows you to create a digital twin of a real product or design, and then uses computational fluid dynamics to predict temperature and airflow. So on the right hand side you can see a real life photograph of a VR headset, and on the left you can see a simulation of a VR headset. You can see the temperature map on the PCB corresponding to areas of high and low temperature. Thermal simulation allows you to solve for airflow and heat transfer, and can consider all three mechanisms of heat transfer: conduction, convection and radiation. If we consider a component sitting on top of a PCB, from its top surface it loses heat to the environment via radiation to the enclosure and convection to the air. From its bottom surface, heat is conducted to the PCB, and then this spreads through the PCB by conduction through the various copper layers and thermal vias, and the PCB also loses heat to the air via convection and radiates to the enclosure. Thermal simulation also allows you to consider things such as transient simulations, so how the temperature and airflow change through time. So you could analyze a product heating up, how long does it take to reach a certain temperature. It also lets you consider multi-fluid simulations, so you can have things like cold plates that are cooled by liquids sitting on top of components. You can consider the effects of solar radiation. Do you need to add solar shielding to your design for it to be able to work in an outdoor environment? And you can also consider things like dual heating, so the heating that occurs in material due to electric current. So I mentioned this earlier, but what is simulation driven design? Well, ideally you will incorporate simulation into the design process at the very start. You will analyze your products in a wide range of scenarios, different environments, different temperatures. You will identify any potential thermal issues. You will then investigate solutions within the simulation tool, and then once you're satisfied the design will work, you'll then create a prototype. You'll measure and test this under a variety of conditions, verify A, that the product works, and B, that your results tally with what you saw in the simulation, and then providing you pass them checks, you will release the product. This contrasts to typical prototype driven design, which is the diagram you can see at the bottom. In this case, you'll design the product, create a prototype, measure and test this, identify issues, you'll fix the issues. This will require a redesign, creating a new prototype, more measurement and testing, and then hopefully there's no issues and you can release, or again you will go through another loop of fixing the issues. And every time you pass through this prototype loop, as we discussed previously, it can cost you tens of thousands of pounds. In reality, simulation driven design isn't going to mean you will release a product after only building one prototype. You may still need to go through this fixing issues loop a couple of times, but you'll be going through it a lot less times than you would with prototype driven design. So, how can thermal simulation help you make better engineering decisions? Well, it gives you a visual representation of temperature and airflow, allowing you to highlight any potential thermal issues. It gives you temperature and airflow throughout the device and not just at discrete points, which is what you would typically get using measurement. You would place, let's say, thermocouples at a handful of points and get data at those positions. With simulation, you can see the temperature distribution throughout the device. Like I said, you can identify overheating and investigate a wide range of solutions. This can be done in a matter of minutes as opposed to a matter of days or weeks if you had to build a prototype, build new parts, and complete tests. And also you can simulate under a wide range of conditions, so some conditions may not be feasible to test in a laboratory, but you can do this within the simulation tool at the click of a button. And these are just some of the design questions that thermal simulation can help you answer. So for example, can two powerful components be placed close together? Is there enough copper in the board to dissipate the heat? Do I need a heat sink on this component? And I'm sure you can think of many more. What do engineers want from a thermal simulation tool? To answer this question, we surveyed over 100 thermal engineers, most of whom were simulation users, in a report called The State of Thermal, and they identified these 5 things as their top priorities for a simulation tool. In at number 5 is more detail. So engineers produce complicated CAD models and they want to be able to use these for the purposes of simulation without needing to simplify them. They want greater automation, so these engineers might be experts on thermal but not experts on CFD, so they want automation built into the tool to help them out with tasks that they may find complicated. They want faster solve times. They don't want to set a simulation running and get results back next week. They want improved results analysis. They don't want it to be a chore to get the results they need out of the simulation tool. And of course, everybody wants improved accuracy. The State of Thermal also identified that 40% of electronics engineers consider thermal simulation to be either too complex or too time consuming, which may go some of the way to explaining why people are considering thermal so late in the design process. And despite 71% of thermal engineers not being completely satisfied with their simulation package, 60% haven't switched provider in over 3 years. Now, Some of this reluctance to change might be due to people not wanting to take the short-term hit of the design process being slowed down by having to learn a new tool, and some of it could be down to the fact that up until recently there was no means of sharing data between simulation tools. Okay, so now I'm going to talk to you a little bit about Six Sigma ET. So Six Sigma ET is our thermal simulation tool. It was 10 years old last year, and in those 10 years we've provided simulation across the electronics industry, everything from LED light bulbs to outdoor electronics to consumer electronics to models of full racks solved in detail. We've also worked with some huge names across the electronics industry, everyone from Qualcomm to Facebook, from Motorola to Bosch. And why do these guys use Six Sigma ET? Well, firstly, Six Sigma ET is fast. Rohde and Schwarz, who are one of our customers, did a comparison between Six Sigma ET and an alternate simulation tool. They solved 12 benchmark cases, and in 7 out of the 12 cases they found they were unable to reach a solution with the alternate tool. So either it wasn't possible, or they'd spent so much time on it and not yet reached a solution that they decided it was unfeasible. Their cut-off time for amount of time spent was 80 hours, which is about 2 working weeks of engineers' time. In the remaining cases, they found that Six Sigma ET was significantly faster. So in the diagram you can see this is just one of the cases, but it took Six Sigma ET 15 hours to reach a solution, including CAD import, gridding, solving and analysing results, and it took the alternate software 45 hours. So if you think you could have ran 3 simulations with Six Sigma ET in the time it's taken to complete one with the alternate software. So to put some numbers on how fast Six Sigma ET is, we can solve up to 750 million grid cells. We can solve a 100 million cell model in an hour. These models can incorporate tens of thousands of objects, and the shape and design of these objects can come from complex mechanical and electronical CAD. Six Sigma ET is detailed. We can simulate everything from a simple concept design, this can be built up using our intelligent modeling objects, all the way up to a full detailed PCB that can be imported from your EDA tool of choice. A full detailed PCB will include the full board layout, the layer stack up, all the thermal vias, all the traces, all the holes, and the location of each and every component. In terms of component modeling, we provide similar flexibility. For a simple concept design, you might wish to model everything as simplified blocks, so this would be a block of silicon with a power dissipation associated to it. We can also model various thermal resistor networks, so these are typically found on component datasheets or can be provided by the component manufacturer. And we can also model a component in detail, so if you happen to be a component manufacturer, you can build a detailed model of your component, including all the subcomponents and their associated materials and power dissipations. Six Sigma ET is also automated. We know that our users may not be CFD experts, and we've tried to build as much automation into the software as possible. So we have intelligent modeling objects that know what they are and how they should behave. We have parent and child relationships between objects, so components know they're associated to particular PCBs and things like that. And we've also automated complicated processes like gridding. This allows non-CFD experts to get good solutions at the click of a button. We've also built as much automation into the post-processing of results as possible. We have a variety of pre-configured views that allow you to access results for airflow and temperature at the click of a button. We also have a feature to automatically generate reports which include all the plots an engineer may wish to see. Six Sigma ET is also very accurate. As part of the development process, it is regularly validated against a wide range of analytical solutions, as well as published experimental data, and it has also been shown to perform well in a variety of studies that have been published by our customers. On the left here, you can see a study by Thales where they simulated a component sitting on a JEDEC test board and compared the simulation data versus measured data, and as you can see from the graph, they show excellent agreement. And also the University of Arlington, Texas, as part of the Open Compute project, validated Six Sigma ET against experimental results, and you can see again excellent agreement. And finally, Six Sigma ET is connected. I mentioned earlier that previously it wasn't possible to share data between simulation tools. However, recently the industry has introduced the ECXML file format that allows for the exchange of data between IcePack, Flowtherm and Six Sigma ET. So now engineers shouldn't feel like they are tied to a particular tool. So that comes to the end of the presentation. Thank you for watching.